In this video, we're going to look at inductor-resistor circuits. These are circuits that have a transient nature. We've already looked at the initial and final state, but we want to look at the specific kind of transient state in the middle. And then we also want to talk about how much energy can be stored using an inductor. So we already know about what happens just after the switch is flipped, right? There's this big resistance to current, and after a long time, you get current flowing. We want to look at that in-between bit, right? So you know already that the current, right, starts out low and goes up. If there's no current through the resistor, then the voltage of the inductor should start out high because all the voltage is across the inductor. And the voltage of the resistor should start out at 0 because Ohm's law says no current, no voltage for a resistor. Then over time, as the current ramps up, so does the voltage, and the voltage across the inductor drops. The format or formula for this is that e to the negative t over tau relationship. 1 minus times I final. We've got the EMF of the battery as the initial value decaying down to 0. And then for the voltage we got of the resistor, we've got, again, EMF times 1 minus e to the negative t over tau. So the big thing is finding the tau value. We're going to use the loop rule going around. We've got the EMF of the battery, the voltage across the resistor, which is from Ohm's law IR. And then for the inductor itself, it's L di dt, right? That's how much EMF there is in a given inductor, as we learned before. So now we're going to separate and integrate this. We're going to get rid of the natural log, and you end up with I as a function of time. The current through the circuit is EMF over R. That's the voltage of the battery divided by the resistance of the circuit. So that's the current, max current in the circuit, times 1 minus e to the negative t over tau. We start with that. Okay. So if that's the case, right, tau equals L over R. And this is what it looks like charging an inductor. So we can fill out page 48 with those things. Sorry. L over R for tau. The current starts at 0 and it goes up to some value. Voltage of the resistor follows that same pattern, and the voltage across the inductor decays down. So the inductive time constant, similar to how the capacitive time constant was RC, here it's L over R, and tau must be in seconds. You can check those units. The other thing to think about, though, is the discharging of an inductor. Again, we're using charging here, kind of in quotes, because it doesn't actually charge. But when you have current running through an inductor, right, and with an inductor, you can't actually disconnect the circuit and then connect it to another one in the same way that you can with a capacitor, because if you break the circuit, then the current will stop flowing. And if the current stops flowing, then it kind of defeats the whole purpose. But what we can see is that the current is flowing, and we have energy stored in the capacitor, stored in that magnetic field. We know that the energy stored exists because when we flip the switch, the current still flows. And this is because it takes work or energy to do this, right? What is the equation? Well, we've got kinetic energy, spring potential energy, capacitive stored energy, and energy stored in an inductor. It's the same basic relationship. 1/2 L, the inductance, times I squared, because I is the thing that matters here. Now, it's not super important you be able to derive this formula, but this is kind of how we go about it. We could do the loop rule, multiply through, and you get the value like that. You can check your units. It does come out to be joules, which is nice. So let's do this an example of how you would kind of think about this. If the switch has been in position A for a long time, it's reached its steady state, and then you move it from A to B, how much total energy will be dissipated by the resistor, right? We know that the current through the resistor, we can figure out what that will be at the beginning, but then it changes over time. So here's what we do. Before you flip the switch to B, the current is 0.9 amps. That's what's going on at the steady state. The energy stored in the inductor is 1/2 Li squared, or about 4 joules. During discharge, all this energy has to go away because at the end, there's no current flowing. So that means all of that energy is turned into heat by the resistor. That's how you think about it, right? So it's not nearly as complicated an idea as you might think. That's the transient state of the inductor, and pretty much our last new concept.